Okay, this is your Chapter 19 video supplement. So at this point, you should have already read the chapter on global atmospheric change. One of the things I want to talk about that isn't covered that thoroughly in your textbook is the greenhouse effect. Now, I did give you a link, as you know, to the entire textbook as opposed to just posting the individual PDFs for the chapters that we're focusing on. But on page 151, which I believe is chapter 7, there are a couple paragraphs there on the greenhouse effect. So you might want to just look at that, but I didn't assign the chapter because there's a lot of information there that we just don't cover. Okay, so what really is the greenhouse effect then? So let's imagine here's the surface of the Earth like this. And we have the sun up here giving off electromagnetic radiation, which was talked about early on. In the introductory section, your module 1. So this electromagnetic radiation is coming through and it's reaching Earth, and let's say this represents kind of the atmosphere. So these rays come through and they're absorbed by the Earth and they bounce back off. And when they bounce back off at a different type of radiation, a different wavelength. We talked about that a little bit. So now some of it gets trapped by these gases. So effectively, these gases are simply absorbing the electromagnetic radiation. Not much different than ozone, which we'll talk about a little bit later in this video, but you should have read about, absorbs ultraviolet light. Ultraviolet light is a form of electromagnetic radiation. So chemical molecules can absorb electromagnetic radiation. So what happens now if we add more of these gases? As I mentioned to you in your slides, and you should have got from your reading, there are different gases that trap heat and absorb electromagnetic radiation that warm the Earth. So these gases are things like CO2 and methane, to name just two. Water is also a heat-trapping gas that we talked about and I mentioned in the slides. So let's imagine now that we've increased the amount of these gases here. So ultimately now what happens is more of this radiation gets trapped and doesn't escape. And that really is the key here, that we're getting more and more radiation that's not escaping. That's what's resulting in this kind of warming effect that we're seeing. So as you increase the concentration of gases like this in the atmosphere, you are effectively going to increase the temperature. And ultimately, increasing the temperature, as you know from your reading, can lead to some other problems with climate change. It's not all about warming. So this is a classic figure I want to show you, and I adapted this from a website, and all the information is given there, and you can actually go to this website and look at this figure if you're interested. So what this is now, what we have here is a line which represents the average temperature from 1961 to 1990. So it's well after the Industrial Revolution. It's after already that we've put in a bunch of heat-trapping gases to the atmosphere. The Industrial Revolution, if you remember from our introduction, ended around 1860. So you see that temperature fluctuates tremendously. And what this is simply is deviations from that average. So you see negative 0.5, negative 1, plus 0.5, 1.5. So these are deviations from that average rather than actual temperatures. And you can see we go back quite a ways here in terms of years. And proxy here means you're not measuring the temperatures directly. Obviously, we didn't measure the temperatures this many years ago, but we can get it from things like tree rings, ice cores, and corals, and we can make measurements in what's called indirectly. That would be our proxy data. It's too difficult for me to really go into explaining how that data is collected, but trust me, there's lots of different ways you can measure temperature like this. So what you see here is this huge rise right here that's occurred fairly recently. And I just want to stress that this really is what disturbs most scientists that study in this area and that are experts in this area and publish in the top quality peer journals in this area. And that is that When climate scientists model these temperature changes, there's so many variables that go into what affects the temperature of the Earth in any given year. Now, we're not talking about weather that changes from day to day or month to month or year to year. We're talking about global climate over hundreds and thousands of years, okay? But what goes into those are similar to what goes into your daily weather, why the weather in Tennessee can change drastically 20 degrees in no time. So what they do is they put all of these parameters. There's lots of parameters that go into these models that predict what will happen to weather on this planet. And things like, cloud cover and ocean currents, okay, and things like this. And what they do is they attempt to model the data. And they keep playing with these numbers because there's ranges to them. There's ranges of cloud cover. There's different predictions on what's going to happen to the ocean currents, different ranges. So they'll put in all different ranges to see how they can best model the data. And when they get a good fit, then they feel comfortable with that model is describing what is actually happening. Well, what concerns most scientists is that the only way they can get their models to describe this, if you will, rapid rise, this is the key to what most concerns most scientists, is the rate of change, not the actual temperature. It's the rate at which this temperature has increased in such a short amount of time. Because if you go back even further than this here, you'll see periods in which we have substantial warm periods. But they increase to those temperatures over much longer periods of time, thousands of years sometimes, as opposed to a very short period of time, what you're seeing here. And their models, their climate models, can only predict this rapid rise right here when they include anthropogenic, that is human input, of heat-trapping gases. They can play with all the other numbers, solar fluxes and currents and cloud cover, and they can never get the models to match the data until they carefully include the human input of heat-trapping gases. So that's really what I wanted to get out of this. And there's several of these types of figures in your textbook to help you understand what's going on with temperature and climate change. Okay, so next I want to talk about ozone chemistry, because this is something that's not really covered much at all in the book, and it is towards the end of the book that you see this. Okay, so ozone, composed only of oxygens, 3 oxygens bound together. It's produced when lightning strikes, but as you know from reading and some of the slides you looked at, this exists in the stratosphere, which is the second layer from the Earth, the troposphere being the first one. It's a natural part of that layer that absorbs ultraviolet radiation and protects us, because ultraviolet radiation can damage your skin, it can damage DNA. So what it basically does is it simply absorbs the ultraviolet radiation, just the same way you saw the heat-trapping gases here were absorbing. This happened to be infrared radiation here that was going back out. That's being trapped here, IR, infrared radiation. This is ultraviolet over here that's being absorbed by ozone. And it does that by simply taking up the energy. And that energy splits the molecule to this. That's where the energy goes. Now that you've split it, it was used to break this bond, and these molecules now have higher energy than ozone. This happens naturally in the stratosphere, and the ozone continually breaks down and reforms, because you can form ozone again by simply going oxygen plus O2 goes to ozone. This happens constantly over and over. In fact, scientists estimate that the average ozone molecule only lasts about 30 minutes before it's destroyed. That's normal ozone chemistry without any human input. Ozone depletion occurs now since we have introduced these chemicals which you read about, chlorofluorocarbons or CFCs. This is a simple CFC. It's a carbon bound with 2 fluorines and 2 chlorines. And what this does, it also absorbs ultraviolet light. So we use this, as was mentioned, things like cooling systems, air conditioning, refrigerators. And when those get thrown away or when they get recharged, whatever, some of this stuff escapes to the atmosphere, and it makes it all the way up to the stratosphere. Okay? And then when it gets up to the stratosphere, see, it's a pretty stable compound. So it's in the troposphere, nothing really happens to it. When it gets up to the stratosphere, this is energetic enough to split it. That's where the problem comes. Because ultimately what happens is this molecule gets split and we get this. And don't just ignore that little dot. It just means it's a radical, which means it's very reactive. It has a single electron. That's the way we designate that. This can then attack ozone. And it gives you this. And what I want you to realize is this chlorine here, which is the key, this reactive chlorine, is going to get recycled so that it can destroy other ozone molecules over and over again. See, it's regenerated again. This is what we call a catalyst. Okay? It catalyzes this reaction right here, and it's regenerated down here. Now it can go and do this all again. So this is the chain reaction that happens over and over again. And scientists estimate that one CFC, by producing this right here, can destroy 10,000 ozone molecules before it goes through some other reaction that removes it from the atmosphere. That's why you get this ozone hole and this massive destruction of ozone. The ozone hole requires special conditions. That's why it only happens over the South Pole and not over the North Pole. There's a lot of different weather conditions and situations that occur with cloud cover and stuff like that that make it ideal, and you get this huge destruction all at once that leads to opening of that ozone into a hole with a lot of it being destroyed. So that's the key. This is a catalyst, speeds up the reaction, it gets recycled again, and this is how the ozone's being destroyed. So, this is a short video for this one. Most of this book does a pretty good job of just getting you through the basic climate change stuff. So, you should have gotten temperature and climate change projections, kind of what we can expect. What are some of the predictions? There are some uncertainty with those predictions. It's important that you realize that. And I think I mentioned that in my slides. What are some of the effects of climate change? Some of that is also mentioned in my slides. I mean, obviously, the obvious things are increasing temperature, which can lead to melting ice. But there's also stuff like spread of disease, impact on agriculture, and stuff like that that is not as obvious. Your book talks about ways in which we can slow climate disruption. Of course, one of the obvious ways, we've already talked about renewable energies and non-renewable energies. We need to move away from fossil fuels and start by moving away from coal. Coal is one of the worst culprits here. It has a lot of problems. If you noticed from our chapter on fossil fuels, it's not just climate change. Move away from coal and other fossil fuels, get towards renewable energies, and maybe do things like capture some CO2 that's out there already to help mitigate some of the effects that are already underway. And lastly, you should know, what causes ozone depletion, what are the culprits, the CFCs, and read about the Montreal Protocol. This is a success story, in some ways an environmental success story that the world came together, was able to come to an agreement with this treaty. And there's been numerous treaties since then or amendments to the Montreal Protocol. Countries have met, and we've been very successful in helping the ozone layer recover. With that, that is the end of your video.